some roofs go up, padlock, in, can read it. And there's an official interface, there's a monitor port, there's a switch where you take your laptop, plug in your laptop, use a certain kind of software, and you can intercept all traffic received from this base station in clear text, including voice, everything, okay? So there's no end-to-end security on GSM. And this is how far GSM security goes. Okay, this is the network, this is where it is secure. And, well, this was broken. This was broken in 98 already. Shamir and other researchers broke this in 98. But what they broke is a theoretical attack. They still required, I think the best attack right now requires 90 seconds of traffic. But that wasn't good enough for us. We wanted to crack anything. We wanted to crack any kind of SMS message that only lasts a couple of milliseconds. And in the end, I mean, most phone calls, over 90% of all phone calls are shorter than 90 seconds. So this attack was, okay, in theory GSM had broken, but practically no one can still break it. So we want to do the practical thing. Okay, about the standards. It all started with A5/1, the strong encryption algorithm. Now, when GSM started in the 80s, they were so excited about it that it had encryption, because the US, they didn't have any encryption, that they thought, oh, this is far too strong, and we can't give it to the Russians, and we can't give it to the Middle East, so we better invent A5/2, which we can crack, and then we can use it, and we can give it to them and sell it to them. And obviously A5/2 was cracked in a minute, and you can real-time just use a computer to intercept the traffic. For a long time in France, there was A5/2 was used so that the government can sniff on their own people. But that's not true anymore. That's still a myth that they're still using A5/2. We verified this with the Tracemo, but they are using A5/1, which doesn't make a big difference because we're breaking it as well. Okay, another attack vector is be aware, your mobile operator knows your key. Okay, this is not your private key. There's no private public key authentication. This is a static shared secret generated by the mobile operator given to you on the SIM card. So somewhere the mobile operator has a database which contains all the keys of all subscribers. Anyone with access to this database can decrypt your traffic. Anyone with access to your SIM card can decrypt your traffic without having to retrieve the key from the SIM card. How it works, the SIM card has an interface where you can tell the SIM card, this is the random that you just received, and this is the GSM packet, generate the key material, keep it secret, don't tell me what you generate, but just decrypt this packet, okay? So with access to the SIM card, everyone can decrypt past conversation happened. So if today, for example, you do a conversation on a mobile phone, and you throw your mobile phone away and your SIM card away, and someone in 2 years takes your mobile phone out of the bin, he can decrypt all conversation you had in the past. Okay? Okay, let's see how A5/1 works. Let me check the time, how we're doing. Perfect. Okay. This is a shift register, A5/1. I'm not bothering with you explaining A5/2 because they are all coming from the same idea. It's a shift register of 64 bits. And what happens is you have your key, which is 64 bits. I'll come to that later. It's 64 bits. And it's fed into the shift registers, and they are clocked. You see 3 registers, R1, R2, R3. And you see these dark registers, these are tap registers. These are clocking registers. And yeah?
Hard to see a little your slide because of all the light here. Is it okay if we turn it off? Does that look?
Don't get scared, okay?
I'm just not sure how to do this yet. We learn as we go. Oh my god. Where's the manual for the
Okay, yeah.
If your laptop turns off now because you
Okay, so you have these clocking registers, and the clocking registers decide when to shift each register to the left or to the right. So let's assume all the registers are filled with some zeros and ones, and you want to clock it for 1 cycle to receive 1 bit of output. So the C1, C3, C2 determine which registers is shift, and this then depends which bits falls off at the end and is used for the output stream. Okay, so it's fairly simple, and it's fed back to the beginning again. There's no new input. It's just always fed back and comes in. And you see these different arrows here. This means that these bits are XORed as well and put back in at the beginning. So you see these registers, the top register is 19-bit long, 22 bits and 23-bit, giving you a 64-bit key state. And well, one obvious attack is when you know the output stream, and you know the output stream because you're intercepting the traffic, and you set R1 and R2, you guess R1 and R2, you can calculate R3. Okay, this is an obvious attack. And the complexity roughly is 2 to the power of 42, which still means it requires you a couple of hours on an FPGA cluster. Not good enough for us. Not good enough. We want to be better than that. Okay, A5/1 encrypts per each frame. Each frame that is sent is encrypted under a different key state. And the algorithm generates 114 bits of cipher stream, which is then XORed with your plaintext, giving you the ciphertext. Okay, so the result is the ciphertext. And to understand, when you read the academic paper from Shami and other people, they say, yeah, you need 90 seconds, but you also need to know the plaintext. It's a plaintext attack, it's a known plaintext attack. You have to know the plaintext. And they say, yeah, you can guess the plaintext. You can maybe assume that each person in the beginning of a conversation says hello, or you can assume that only one of the person is speaking at the same time. So it gets really rather complicated. I mean, it's a theoretical attack, it's not a practical attack. But there's something much easier what they didn't know. We are coming from the GSM. We are not coming from the crypto community, we are coming from the GSM community. And we know that every GSM message is padded. It has to be 23 bytes long, 23 octets. So each message, if you can't fit enough data in there, is padded with the fixed byte, OX2B. Okay, so we have a lot of known plaintext. And in fact, the first message that sends is almost everything is padded except 3 octets. And also these 3 octets are always the same. So the first message, we have always known plaintext. And our attack only needs the first message, and we can crack. More to that later. Oh yeah, I said that already. Okay, our attack. We use a combination of rainbow table attack and others. So some of you might have heard of rainbow tables. If you come from the academic field, they're more known as CMTO, time memory trade-off attacks. And they were invented by Hellman in the 80s. And to give you a kind of understanding what they're doing is, let's go back to this one. You have a certain state, and this state generates 64-bit of output. Let's assume it only generates 64, not 114-bit. And what would happen if you take this output again, and use the output as a state and generate another 64-bit. And you take again the output as a state and generate another 64-bit. And you do it a couple of million of times until you hit a distinguished point. For example, until the first 20 bits output are 0. Okay? Then you have a start. You started with a fixed state. You go round, around until an endpoint. Now what happens when you sniff a cipher stream, you do the same with the cipher stream. You take the cipher stream, use it as an input again, and you do it as long until you have hit this distinguished point, until the first 20 bits are 0 of the output. And then you know, probably, hopefully, then when you start again with the original start point, and you do this again, you will hit exactly the state. You will hit the output. Okay, and this is called time memory trade-off attacks. And this is basically what we are doing. And we are modifying a little bit to work better on GSM. And A5 has a lot of collisions, so we had to get around this problem. Ultimately, last year, 6 months ago, we thought we can do it on 5 terabyte, and we would require 4 hours for one session. Now we have optimized this. We can do it on 2 terabyte, and we only need 1 hour for one session. And the complexity is 2 to the power of 30. So the first attack that I explained, the Rowan-Anderson attack, where you guess one of the registers, was 2 to the power of 42, and we brought it down with the TMTO attack to 2 to the power of 30, which is good. Now, okay, let's go back to the TMTO attack. The simplest thing with the TMTO attack, or to attack this, is you would take a state, you would generate 64-bit of output, and you have the output. And you save these tuples. So you always save the start state and the output. Start state, output. So you would ultimately have to store 2 to the power of 64 tuples of each 128-bit long, which is quite a lot of data, and you can't really do it. And it's also quite a lot of processing power, because you have to do this 2 to the power of 64. Now, this is a stream cipher. And this helps us a lot, because, as I said earlier, you generate the output, and you check your cipher stream if you hit this output. But because you have 114 bits, you don't just do this from bit 0 to bit 63, you also do this from bit 1 to bit 64, and from bit 2 to bit 65. So you can do this 50 times. And because you have four GSM frames, you can do it 100 times. So this brings down our pre-computation time dramatically. We don't have to pre-compute 2 to the power of 64 records. We only have to pre-compute, well, far less, 2 to the power of 50 something, which is great, because then we can do it on an FPGA cluster in 60 days. And this is only the pre-computation. TM2 is always done in the pre-computation phase, where you generate these tables, and in the online phase. And the online phase is the actual attack, where you use the table to look up the values. And the online phase for the demo buster will take 1 hour in total. Now, we thought, okay, that's quite good, but we also have a commercial solution available. It's the A5 buster, and this will be available in 08. And we target to get this attack done under 30 seconds with a 95% probability, and it will be using 28 terabytes and a couple of FPGAs. And this will be the real-time online phase attack. The A5 demo attack, we probably release around the same day. We will make these tables public on the internet. We are hosting it on the Internet Archive project. John Gilmer offered us this, and that's great because he said they have a couple of petabytes kicking around they're not using. So, yeah, we do that with them. Okay. Let's think about the future. This is all nice and fine, we can crack GSM, but that's just a small thing. You can do more with GSM. You can do more when you have an USRP. You can start sending. You can pretend being a base station. You can other people having logged into your computer, and you forward their calls, which is exciting. You can generate your own baby cell. Imagine you have a conference and you just serve your own mobile network. Everyone can do phone calls for free. You're in the city, you give the entire city free mobile phone calls. I don't know, it's not really legal, but you could do it. Well, obviously then the typical security assessment things, you can do man-in-the-middle attack, you can track people. Oh, tracking people is interesting. People always assume to track someone, you need 3 antennas and you do some kind of triangulation. That's not true. You can do it with one USRP. And that's great because the base station already gives you the information how far a mobile subscriber is, the distance from a mobile subscriber to a base station. So this is already known. Because you receive this information, you know where the base station is, you know the distance to your machine, you can triangulate them with just one receiver because you get a lot of information already. You get the phone numbers, you can get the phone numbers if interested in it. You can try to access the mobile operator database. A typical, what can we do if we have access to the network? What's our next thing? What's a threat? What's a threat to the mobile operator? The threat to the mobile operator is that someone might take a look at the database. Someone might send packets that were not supposed to be sent. Buffer overflows come to mind, denial of services, who knows? I don't. Well, obviously free calls, we talked about that. And the next big thing is UMTS and 3G. Femtocells and picocells are already selling target boards, so you can experiment with that network as well. And ultimately, join us, join our effort. Feel free, everything is open. The last thing that we are currently using for sending and receiving traffic is the OpenTSM, which was a Spanish phone, which the source code is on the internet, and you compile the firmware on your own. You have access to the DSP, you have access to the baseband processor, and you can do a lot of things, and the things cost around 40 euro or so. And it's maybe a cheaper solution than the USRP. Ultimately, the USRP is more powerful because you can do more things with it. But for an entry-level GSM, interceptor, sending, pirate, whatever, OpenTSM is a good choice. And that's it. Thanks a lot. If there are any questions, please ask some questions. I'm sure there was something not so clear. Please.
I'm not sure if I missed it, but I think you didn't say anything about the security of SMS in this context.
Yes, okay. SMS, it's defined in the E2 documents as it's optional and left to the operator to encrypt it or not. So